Can you map out all the islands in a complex network? Number of connected components in an undirected graph is a pattern mastery 100 essential. Frequently asked at Google, Facebook, and Amazon to test your ability to traverse graphs and count isolated clusters. Over 30% of candidates overlook singleton nodes or double count connections. Master this, and you'll be equipped for any graph or network connectivity problem. Let's solve number of connected components in an undirected graph using the basic method, so you never miss a node or count. Integer n, number of nodes, list of undirected edges. Integer, total number of connected components. Imagine mapping isolated local networks in a city, or identifying separate user groups in a social app. An interviewer might ask, how would you count all the isolated clusters in a computer network or database? What's tricky? Need to visit every node, even those with no connections, singleton components. Must avoid double counting, mark each node as visited as you explore. Both DFS and BFS work well here. Union-Find, DSU, is great for optimizing. Build an adjacency list from the edge list. Initialize a visited set or array. Loop through all nodes 0 to n1. If a node isn't visited, it's the start of a new component. Increment the count. Run DFS/BFS from that node, marking all reachable nodes as visited. Continue until all nodes are visited. Let's clarify. Single nodes with no edges count as their own components. Each DFS/BFS call finds exactly one component. Edge cases. Disconnected graph, multiple clusters. All nodes connected, one component. No edges, all singletons. Build an adjacency list from edges. Initialize a visited set or array for every node from 0 to n1. If not visited, increment components count. Run DFS/BFS to mark all reachable nodes as visited. Return components count. Let's try to implement it using solution 1. Time complexity, O(n plus e). The concept discussion. We're counting how many separate groups exist in an undirected graph. A connected component is a set of nodes where every node can reach every other node in that set. The strategy is straightforward. Build an adjacency list, then scan through all nodes. Whenever we find a node we haven't visited, that means we just discovered a new component, so we increment the counter and run a DFS from that node to mark the entire component as visited. Repeat until every node has been visited. This function builds the graph, then repeatedly launches a DFS from each unvisited node. Each launch corresponds to one connected component. First, we turn the edge list into an adjacency list so it's easy to find neighbors quickly. Since the graph is undirected, every edge goes both ways, so we add each endpoint to the other's neighbor list. We create a visited set to remember which nodes we've already explored, and a components counter to track how many separate groups we've found. This DFS is implemented with a stack, so we don't rely on recursion. Starting from one node, it keeps expanding to all reachable neighbors, marking them visited. When this finishes, it means we've fully covered that node's entire connected component. Now we loop through every node. If a node hasn't been visited, that means it belongs to a component we haven't discovered yet. So we mark it visited. Run DFS to visit everything connected to it. Increment components because that DFS launch represents one whole connected component. After scanning all nodes, components is the total number of connected components, so we return it. And that's how this algorithm works. It first builds the adjacency list and initializes a visited set plus a component counter. Then it scans every node and launches a DFS from each unvisited node to mark its entire group, counting how many separate groups exist. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, labeled 0 to 4, and the edges 0, 1, 1, 2, 3, 4. Each edge shows a two-way connection, since this is an undirected graph. First, we build an adjacency list so every node knows its neighbors. Then we loop through every node, and whenever we find a node that hasn't been visited yet, that means we've discovered a new connected component. At that point we run an iterative DFS using a stack to visit everything reachable from that start node. Here's what happens. Starting at 0, DFS reaches 1, and from 1 it reaches 2. So, 0, 1, 2 is one full component. Later, when we get to node 3, it hasn't been visited yet, so that's a second component. DFS from 3 reaches 4, so 3, 4 becomes the second component. No other nodes are left unvisited after that. And that's exactly what our program outputs, too, matching the expected result. The output makes perfect sense because the graph is split into two separate groups, one cluster of 0, 1, 2, and another cluster of 3 to 4, with no edges connecting the two. So, Our implementation is correct. The algorithm accurately counts connected components by scanning all nodes and using DFS to mark each group. Efficient and accurate. Let's try to implement it using solution 2. Time complexity. O(n plus e). The concept discussion. With Union-Find, we treat each node as starting in its own separate group, so initially we have n components. Every edge, u, v, tries to merge the groups containing u and v. If they were in different groups, merging reduces the total component count by 1. If they were already in the same group, that edge doesn't change anything. After processing all edges, the remaining number of groups is exactly the number of connected components. This function uses Union-Find to merge nodes into groups, shrinking the component count each time a real merge happens. First we set up Union-Find. Each node starts as its own leader, meaning every node begins in its own component. The rank array helps us keep the structure balanced so our operations stay fast. Find tells us which group a node belongs to by returning its leader. The extra improvement here is path compression. After we discover the leader, we rewrite pointers so future lookups are quicker. Union tries to connect two nodes by merging their groups. If both nodes already share the same leader, they're already in the same component, so nothing changes and we return false. Otherwise, we attach the smaller ranked leader under the bigger ranked leader to keep the structure shallow, and return true to show a merge really happened. This is the counting trick. Start with n components, because each node alone is its own component at first. Then for each edge, if Union successfully merges two different components, we reduce the component count by 1. If the edge connects nodes already in the same component, we don't subtract, because the number of components didn't change. After all edges are processed, components is exactly how many connected groups remain in the graph, so we return it. And that's how this algorithm works. It first initializes every node as its own component using Union-Find, then it processes each edge to merge components and decreases the count only when a real merge happens, leaving the final number of connected components. Efficient, simple, and elegant. Let's test our function with n equals 5 nodes, 0 through 4, and these edges, 0, 1, 1, 2, 2, 3, 3, 4. This is an undirected graph, so each edge connects both ways. S solution uses Union-Find. We start by assuming every node is its own component. So, components equals n equals 5. Then we process each edge and union the two endpoints. Union 0, 1 merges two separate sets components becomes 4. Union 1, 2 merges another new node into that set components becomes 3. Union 2, 3 merges again components becomes 2. Union 3, 4 merges again components becomes 1. Since every union here successfully connects two previously separate groups, we keep decreasing the component count, and by the end, all nodes are connected in one chain. And that's exactly what our program outputs, 1, matching the expected result. That output makes perfect sense because the edges form a single connected path, 0, 1, 2, 3, 4, so there's only one connected component. So, our implementation is correct. The algorithm accurately counts components by starting with n groups and reducing the count on each successful union, efficient and accurate. Alright, quick recap to wrap up number of connected components. We're given n nodes and undirected edges, and we want to count how many separate groups exist. A connected component is simply a set of nodes where every node can reach every other node in that group. And yes, this includes isolated nodes that have no edges at all, because those still count as their own component. The core challenge is making sure we cover every node, even the ones with no neighbors, without double counting anything. That's why we rely on a visited tracker. Once a node is part of a discovered group, it shouldn't be processed again. From there, DFS or BFS naturally explores one whole group at a time, and we also noted Union-Find as a strong alternative that merges nodes into groups efficiently. The plan was, build an adjacency list from the edge list, keep a visited set or array, then scan nodes from 0 to n, 1. Every time we encounter an unvisited node, that means we've found a new component, so we increment the count and traverse outward to mark everything in that component as visited. We started traversal from each unvisited node, marked nodes visited as soon as they were discovered, and continued until the entire component was explored. The solution ran cleanly on LeetCode with no errors. We verified it works for disconnected graphs and fully connected graphs, correctly counts isolated nodes as their own components, handles graphs with no edges, and all test cases passed. The key takeaway is, one full traversal equals one component. Every new unvisited node signals a new group. Whether you use DFS, BFS, or Union-Find, the idea is the same, and once you've got this down, graph counting problems start feeling easy.